Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from Department of Physics, Central University of Haryana. Today we are going to discuss about a module, Material Systems and Matter Waves, under the paper Quantum Mechanics 1. So students, let us see what we are going to learn in this module. Firstly, we'll try and understand the Bohr model of the atom and explain the atomic spectra of hydrogen. Secondly, to show how Frank Hertz's experiment supports the Bohr model. Thirdly, learn the Sommerfeld's generalization of quantum rules. Fourthly, to understand the concept of space quantization through Stern-Gerlach experiment. Fifthly, to know the limitations of the Bohr-Sommerfeld model with respect to the actual atomic model that is now existent. And finally, learn the concept of de Broglie waves associated with matter and its experimental verification, that is, the matter waves. Now, coming on to the basics, what happened was that there were parallel developments which were happening which led to the recognition of the dual nature of electromagnetic radiation as was described in the preceding module. However, equally important and significant were the discoveries that were made around the same time, revealing the fundamental nature of material systems and what they were made of. In this module, we give a brief review of the earlier attempts made to understand the structure of the building blocks of matter with a view to explain the discrete characteristic spectrum of radiation associated with each element. The subject matter described here basically constitutes what is known as the elements of the old quantum theory. Hydrogen, being the simplest of the elements known, no wonder, was the area where most of the earlier theoretical attempts were made and was the most efforts were made to understand exactly what was the spectrum of the hydrogen atom and how the spectrum could be explained. So, in order to explain the spectrum of the hydrogen atom, it was necessary to first understand the atomic structure of the hydrogen atom. However, all the earlier theories, that is, the classical theories, were inadequate to explain this atomic structure and the spectrum of the hydrogen atoms. Thus, while the theory, that is the quantum theory, incorporates quantum concepts of discrete energy values assigned to the atom, however, it also uses some of the old suggestions and theories in place. The suggestion that it picked up from the quantum theory was that was made by Planck and also accepts the Einstein's energy relation, which is E is equal to h mu, where h is the Planck's constant and mu is the frequency. Now, this is the relation between the energy of a quantum and the frequency of radiation. Yet, it is essentially based on the laws of classical mechanics, retaining the classical picture of well-defined particle orbits. Atomic structure and the atomic spectra. Study of atomic emission and absorption spectra showed that these spectra consist of discrete lines both in the visible and the invisible region, that is, in the infrared and the ultraviolet region. As an example, if we look at the spectra of the hydrogen atom, we see that there are 4 distinct lines in the visible region, besides a number of lines in the infrared and the ultraviolet region. In order to understand the atomic spectra, it was necessary to first understand the atomic structure. The first concrete step towards fixing the atomic structure was made by J.J. Thomson when he discovered the electron in 1897. He then put forth an atomic model which assumed the atom to be something like a pudding. That is, the protons and the electrons were all mixed together. However, this view changed when Rutherford performed his famous alpha particle scattering experiment in 1911. Rutherford thought that when he bombarded the gold foil with alpha particles, he expected that the alpha particles should get scattered randomly. However, the experimental findings were vastly different from what he expected. This experiment showed that most of the alpha particles passed through the gold foil without any deviation. Some alpha particles suffered minor scattering, while only a very few alpha particles suffered major scattering, with angle of scattering lying between 90 degrees and 180 degrees. This led Rutherford to conclude that atoms have a very small core, which was later called the nucleus, which contains all the positive charge, while the rest of the atom has electrons distributed in it. This is the nuclear atom model. Students, now let us discuss what the Bohr's postulates for the structure of the atom were. He made two important postulates regarding the structure of the atom. The first postulate was that the electrons revolving about the nucleus were only permitted to revolve in certain allowed orbits in which the angular momentum of the orbit was an integral multiple of h cross, where h cross is equal to h by 2 pi and h is the Planck's constant. And this incorporates the idea of discreteness of energies as proposed by Planck. The second postulate was on the emission and absorption of radiation in discrete quanta, and it embraces the Einstein relation between energy of the quantum and the frequency mu of the photon. As a consequence of these postulates and using the classical methods, Bohr obtained striking agreement of the model with the observed spectral lines of hydrogen-like atoms, and he could also predict that how and what is the possibility of the transitions between the different energy levels, and gave the exact condition for such transitions, where he said that all transitions are not possible and the transitions are only possible between such orbitals as were defined in the first postulate. Frank-Hertz experiment. The existence of such discrete energy levels was confirmed by the Frank-Hertz experiment on the scattering of a beam of monoenergetic electrons by atoms. James Frank and Gustav Hertz, who was a nephew of Heinrich Hertz, bombarded the vapors of known elements with electrons, where the energy of the electron was controlled. As the potential of the incident electrons was increased and the electrons bombarded the atomic vapor, it was seen that the collisions were elastic. However, beyond a certain energy, the electron kinetic energy drops suddenly, which was reflected in the drop in the plate current that was being recorded in order to visualize the kinetic energy of the electrons. This sudden drop in the energy of the electrons shows that the electrons have undergone inelastic collision with the vapors of the different materials, and that the amount of energy lost by the electron is given to excite the atoms of the vapor. Similar drops in plate current, which meant similar drops in the kinetic energy of the electron, happens as the initial incident energy of the electrons is increased by increasing its potential. And what was observed was that these drops happened at specific values of energy, which was exactly equal to the amount of energy required to excite the atoms of the vapor to the first excited state or the second excited state, and so on. So, if the initial energy of the incident electrons is E0 and the energy of the first excited state is E1, then the amount of energy lost by the electron is E1 minus E0. Similarly, if E2 is the energy of the second excited state, then the amount of energy lost by the electron is E2 minus E0. Sommerfeld's generalization of quantum rules. Despite its many successes, the Bohr model of circular electron orbits could not explain the fine structure of the spectral lines. Bohr's quantization condition of the orbital angular momentum was valid only in the case of circular orbits and could not be used in more complicated cases. In fact, this condition is a special case of integral over P(dq) is equal to nh, where q refers to the generalized coordinates and p is the corresponding canonically conjugate momentum. In case of an electron revolving about the hydrogen nucleus in a plane elliptic orbit, the nucleus at one focus, the two conditions are integral p phi d phi is equal to n phi h and p r dr is equal to n r h. Bohr theory suggested that the electron orbits are elliptical with nucleus as one of its focus and that the circular orbit was a special case. In the equation that Sommerfeld gave, n phi and nr are the integers where n phi represents the azimuthal or angular momentum quantum number. This quantum number, that is, the angular momentum quantum number, provides us the quantization of the orbital angular momentum. The other integer, that is nr, refers to the radial quantum number, and the radial quantum number gives us the quantization of the radial momentum. The total quantum number n of the Bohr theory is now given by n is equal to nr plus n phi, and n is the total quantum number. The first Sommerfeld condition simplifies to p phi is equal to n phi h cross, since phi is the azimuthal angle, that is, the angle which the radial vector makes between the semi-major axis and the electron. The expression for the total energy comes out to be exactly the same as obtained for circular orbit by Bohr. Now, as we move forward our discussion about Sommerfeld's model, we come to the two general properties that Sommerfeld put forth. The first is degeneracy of the energy levels of the system. Since quantized elliptical orbits in a given plane are characterized by two quantum numbers, that is nr, which is the radial quantum number, and k, where k is the wave vector, and associated with the azimuthal or the angular momentum quantum number n phi for a given value of the principal quantum number n. there are different states, that is, different elliptical orbits of different eccentricities corresponding to k is equal to 1, 2, 3, and so on till n, where n is the principal quantum number. All these have the same energy. That means that the principal quantum number n, so long it remains unchanged, the energy also remains the same, even though you may have these different elliptical orbits that are associated with the same principal quantum number. For example, for n is equal to 2, we can have k is equal to 1 or 2, giving a twofold degeneracy, which means that both these states, k equal to 1 and k equal to 2, would have the same energy for n equal to 2. The second postulate or the property that Sommerfeld gave was the removal of degeneracy when symmetry is broken. This is due to the variation of speed of the electron in the orbit, inducing corresponding changes in the mass given by the theory of relativity. So what is happening is actually that in the elliptical orbits, as the electron moves, because of the relativistic effects, the mass does not remain constant but changes. And because of the variation of mass, what happens is that there is a variation in the speed of the electron. And as a result of these two, the symmetry gets broken. Space quantization and Stern-Gerlach experiment. Space quantization arises from the possibility of various orientations for the angular momentum vector with respect to a fixed axis. This axis may refer to the direction of some externally applied field, say, for instance, the magnetic field. For each value of the angular momentum vector L, the magnetic angular momentum number ml has 2l plus 1 different values corresponding to 2l plus 1 different orientations of the angular momentum vector L with respect to a fixed axis, say the z-axis, which may be the axis of the applied external field, that is, the axis along which the applied external magnetic field is there. This is due to the fact that each such orientation has a magnetic moment associated with it, while the amplitude or the magnitude of the angular momentum vector gives the quantization of the angular momentum magnitude ml, that is, the magnetic angular momentum number gives the quantization of the angular momentum direction or the space direction. Here, the value of the magnetic quantum number m varies from -L, -L plus 1, so on till 0, 1, 2, till L minus 1, and finally L. If we look at the figure here, we see the values of m for L equal to 2. In all, there are 5 values of m corresponding to m equal to -2, m equal to -1, m equal to 0, m equal to 1, and m equal to 2, where theta is the angle between the z-axis and each of these possible values of the magnetic quantum number. Principle of Stern-Gerlach experiment. The experiment is based on the fact that an atom having non-zero orbital angular momentum has associated with it a magnetic moment mu in the direction of the orbital angular momentum L. Such an atom, when placed in a magnetic field, produces a torque tau, which is the cross product of the magnetic moment mu and the magnetic field, that is, the external magnetic field. Such a torque acting on the angular momentum vector is known to have a gyroscopic effect, that is, it would try to align the magnetic moment and hence the angular momentum vector along the direction of the magnetic field. However, if the magnetic field is not uniform, that is, its strength varies as it moves along the position coordinate, or in other words, the strength of the magnetic field is spatially varying, then the magnetic moment of the electron experiences a net force that would act on the atom. Now, consider a magnetic field along the z-axis and its strength increases along the positive z direction, so that a force mu z is equal to del b by del z, that is, partial derivative of the magnetic field with respect to the z-axis acts on the atom. Now, when the beam of atoms pass through a field which is perpendicular to its direction of motion, that is, to the z-axis, then the field causes a splitting of the beam of atoms into two distinct directions. One direction is along the positive z-axis and the other direction is along the negative z-axis, demonstrating the conformation of space quantization. A force acts on the atoms and would cause the atoms to be deflected along the positive or the negative z direction. The amount of deflection would be proportional to the value of mu z. If we look at the figure, we see that a stream of atoms is moving along the positive x-axis. There are two plates which are acting as the electromagnets, providing the necessary magnetic field along the z direction. And at the other end of the setup is a screen on which the stream of atoms is incident. In the absence of a magnetic field, the stream of atoms would simply hit the screen along the positive s-axis on a particular point. However, when the external magnetic field, which is spatially varying, is switched on, then the stream of atoms would either get deflected towards the positive z direction or the negative z direction, depending upon the value of the magnetic moment, or Lz. In case the values of the magnetic moment were continuous, then what one would have expected on the screen would have been a continuous spread of atoms along the xz plane. However, when Frank however, when Stern-Gerlach performed the experiment, they found which was very much different from what they were expecting. Instead of a continuous spread along the xz plane, what they saw were two distinct lines, one along the positive z-axis and the other along the negative z-axis on the xz plane. This splitting of the stream of atoms into these two distinct separate streams showed that the values of Lz or mu z were not continuous but were discrete, and this confirmed the space quantization, the hypothesis that matter, just like light, also has a dual nature, that is, Matter also exhibits wave-particle duality. He suggested that material particles having energy E and momentum P could be represented by the following equations. The equation for energy is E is equal to h mu or h cross omega. Here E is the energy of the material particle, and h is the Planck constant. Mu is the frequency of the matter wave associated with this particle. H cross is h by 2 pi, and omega is the angular frequency given by mu into 2 pi. Similarly, the expression for the momentum vector is given by p vector is equal to h cross k vector, where p denotes the momentum of the particle, h cross is equal to h by 2 pi, where h is the Planck constant, and k vector is the wave vector, where the modulus of k is given by 2 pi by lambda, and lambda is the wavelength associated with the wave of the material particle. Thus, using these relations, de Broglie found a direct relation between the momentum p of the material particle and the wavelength lambda associated with the wave of the material particle. This relation is given by lambda is equal to h by modulus of p vector, which is equal to 2 pi by modulus of k vector. This relation is called the de Broglie relation for matter waves. De Broglie explained the Bohr atomic model by visualizing the electron orbits as standing waves associated with the wave nature of the electron, and further stated that only these orbits were stable for which the orbit was a standing wave, where the wavelength lambda was the wavelength associated with this wave of the material particle. This can be visualized from the figure that is given, where it is shown that the orbit of the particle, that is the electron, is a circular or an elliptical orbit, and there is a continuous standing wave which depicts the wave property of that electron, and it is shown that this wave is a standing wave. Experimental verification of matter waves. The experimental confirmation of wave nature of particles was done by two different experiments, one that was performed by Clinton Davison and Lester Germer in US in 1927, and the other which was done by G. P. Thomson in England in 1928. These two experiments independently confirmed the wave nature of particles by demonstrating that electron beams are diffracted when they are scattered by the regular atomic array of crystals. Davison and Germer were studying the scattering of electron beam from a nickel target when an accident happened and air entered the chamber in which the target, that is, nickel, was kept. This led to the oxidization of nickel. In order to clean the nickel target, they heated it in an oven and placed the target back in the chamber. Now, when they again started performing the experiment, they saw something that was drastically different from what they were expecting from the classical theory. Classical theory suggested that the scattered electrons will emerge in all directions with only moderate dependence on the intensity of the incident electrons and even less on the energy of the incident electrons. However, striking maxima and minima of electron intensity in scattered beam was found whose position depended on the incident electron energy. A strong peak was found to have appeared in the intensity of the scattered electron for an accelerating voltage of 54 volts at a scattering angle theta is equal to 50 due to the constructive interference from the different layers of the regularly spaced atoms of the crystal. This happened because the heating of the nickel target to remove the oxidation had converted the small crystals that were present in it into one large single crystal of nickel. And thus, such a constructive interference from different layers, that is, such a diffraction pattern from different layers of the crystal, much like that one observes in X-rays from different planes of the crystal, was observed. So students, now let us sum up what we have learned in this module. First, we have understood the Bohr model of the atom and explained the atomic spectra of hydrogen. Secondly, we also showed how the Frank-Hertz experiment supports the Bohr model. Then, we learned the Sommerfeld's generalization of the quantum rules and also tried to understand the concept of space quantization through the Stern-Gerlach experiment. Then, we also discussed the limitations of the Bohr-Sommerfeld model of the atom. And finally, we discussed and learnt the concept of de Broglie waves associated with matter. That is, that matter also has a wave nature, and such waves are called matter waves. And finally, we discussed the experimental verification of matter waves or the de Broglie waves that are associated with matter through the experiments that were conducted by Davison and Germer in 1927 and G.P. Thomson in 1928, which clearly showed that matter also has a wave-particle duality or has a dual nature. That means it is exhibiting both particle nature as well as wave nature. Thank you.